Hi everyone, and welcome to this lesson. Today we're diving into one of the most essential topics in computing: binary numbers and data units. By the end of this video, you'll be able to confidently define digital data units like bits and bytes, and understand how computers use binary to represent all kinds of information. We'll also look at how to convert numbers between the systems we use every day, called denary, and the binary number system that computers rely on. We'll keep things practical with lots of relatable examples. So let's get started. Okay, so a quick warm-up. Imagine a code that only uses two symbols, 0 and 1. That's binary. Ask yourself, what do these two numbers actually represent? The answer is that they represent two simple states, on or off. Think of a light switch. It's either on or off, right? That's exactly how computers think, just with billions of these switches flipping between 0 and 1 at lightning speed. And how many different values can you make using just two options? Well, that depends on how many switches or bits you use. But we'll come to that in a moment. So why do computers use binary in the first place? It's because of how they're built specifically, how their electronics work. Inside a computer, everything is based on electrical signals. A signal is either flowing, meaning it's on, or not flowing, meaning it's off. These signals are controlled by microscopic components called transistors. Each transistor acts like a tiny switch. If it's on, it represents a 1. If it's off, it represents a 0. Your computer has billions of these switches, all working together to store data, run software, and carry out instructions. So binary isn't just a code, it's a direct reflection of how computers operate at a physical level. Binary is what we call a base 2 number system. That simply means it only has two digits, 0 and 1. We're used to base 10, also called denary, which has 10 digits, 0 to 9. But for a computer, binary is ideal. Every 0 and 1 can be matched to an electronic state, off or on. This makes it simple and reliable. Here's a neat example. The letter A on your keyboard. In binary, that's 01000001. And the number 5, that's 00000101. All the images, music, and videos you use on your devices are really just very long strings of zeros and ones under the hood. Let's imagine a basic electrical circuit. Picture a battery, a switch, and a light bulb. When the switch is closed, electricity flows and the bulb lights up. When the switch is open, no current flows and the bulb stays off. That's exactly how a bit of data works. On means 1, off means 0. Multiply this simple idea across billions of circuits, and you get a powerful computer capable of incredible things. So every time you type or click, your device is flipping thousands, maybe millions of these little switches. Now, let's talk about data units. The smallest piece of data is a bit. It's either a 0 or a 1. Just like a coin can only be heads or tails, a bit has only two possibilities. Put 4 bits together and you get what's called a nibble. Stack 2 nibbles, so 8 bits, and that's a byte. 1 byte is enough to represent a single character on your keyboard or device, like the letter A. From there, we scale up. A kilobyte is about 1000 bytes. A megabyte is around 1000 kilobytes. A gigabyte is 1000 megabytes, and it keeps going, terabytes, then petabytes. To remember the order, try this. Kittens make great tech pets. To make these units more relatable, let's connect them to the files you may use every day. A short tweet, or what used to be called a tweet, is about 280 bytes. An MP3 song is around 4 megabytes. A full HD movie is roughly around 4 gigabytes. A school network backup, that could easily be a terabyte or more. Knowing these sizes helps you manage storage, predict download times, and make smarter tech choices. Let's say you only have one switch, a single bit. That gives you two possible values, 0 and 1. If you have 2 bits, now you can make 4 different combinations, 0, 0, 0, 1, 1, 0, and 1, 1. 3 bits gives you 8 possible combinations. 4 bits will give you 16. The simple rule is that the number of combinations is 2 to the power of the number of bits. So for 8 bits, you get 2 to the power of 8, which is 256. That's why a byte of 8 bits can represent any number from 0 to 255. So to put it simply, as the number of switches increases by 1, as we can see on the left-hand side, so 1 to 8, we can see on the right-hand side that the possible combinations of states doubles each time with an increase of a switch. We live in a denary world, which is base 10. We count from 0 to 9 and then roll over to 10. Computers live in a binary world, which is base 2. They count 0 and 1, then roll over to 1, 0, which is 2 in denary. The idea is the same. It's just the base 10, it's just the base that's different. You'll soon see why converting between the two systems is just a matter of applying the right method. In the denary number system, every digit has a place value. The first digit is the units column. The next digit is the tens column. Then the third column is the hundreds column, and then we have the thousands and so on. Binary works the same way, but using powers of 2. So the first column is 2 to the power of 0, which is just 1. 2 to the power of 1, which is 2. Then it's 2 to the power of 2, which is 4. 2 to the power of 3, which is 8, and so on, up to 128 for 8 bits. This is the secret behind binary conversions, which we'll practice next. Let's say you have the binary number 00111001. To convert it, you line up the place values which are in the orange color. So the numbers from right to left will be 1, 2, 4, 8, 16, 32, 64, and 28. Next, you will write the binary digits underneath. You will then add up the place values where there is a 1 underneath them. We can see from the example on the screen that 00111 has ones under the 32, 16, 8 and 1 spots. Therefore, what we need to do is add these values together from the place value. So 32 plus 16 plus 8 plus 1. When we add those numbers up, it gives us the denary number 57. So the binary number 00111 equals 57 in denary. So binary, not all bits carry the same weight. The leftmost bit is called the most significant bit. It has the highest value. The rightmost bit is the least significant bit. It has the lowest. This matters when understanding how values are stored, or when a system needs to prioritize certain bits. Just remember, the closer to the left, the more important the bit's value. Let's go back to that binary number 00111 Imagine this as a row of 8 small lights or LEDs. Each light represents a bit. If the bit is 1, the light is on. If it's 0, the light is off. In this case, 4 lights would be on and 4 off. It's a visual way to imagine how binary data can be seen in hardware. This pattern might represent a number, a letter, or even part of an image pixel, depending on the context. Let's say you want to turn the number 28 into binary. Start with the largest binary place value less than 28. So in this example, it will be 16. 28 minus 16 is 12. So the bit for 16 equals 1. Next, 8 fits in 12. 12 minus 8 equals 4. So bit for 8 should equal 1. 4 fits exactly into 4. So 4 minus 4 is 0. So the bit for 4 should equal 1. The remaining bits, 32, 64, 128, etc., are too large. So they're all 0. So you write it out as 0001110. So that's 28 in binary. Each time you add a bit, you double the range of numbers you can represent. 8 bits, that's 256 values. It's 0 to 255. Just bearing in mind that binary or computers will start counting from 0. 16 bits will give you over 65,000. 32 bits will give you over 4 billion. This is why games, apps, and files can be managed so efficiently. Computers can handle huge numbers with just a few bits. Let's bring this into the real world. Older software, like early versions of Excel, used 16-bit systems, so they were limited to around 65,000 rows. Modern software uses 32-bit or even 64-bit systems, which means billions or even trillions of possible values. As a developer or user, this matters when choosing data types or dealing with large files. Before we finish, let's do a quick recap quiz. What 2 values can a bit store? How many bits make a nibble and a byte? What units come after kilobyte, megabyte, gigabyte, terabyte, or petabyte? What are the binary values for 0, and 255 and 39. Pause the video here and have a think about some of these questions. And once you've done, press play to check out the answers. Awesome. If you understood these, you're well on your way to mastering binary and data units. Thanks for watching, and don't forget to like, subscribe, and share, and keep learning. Bye for now.